All right. Okay, close them up. I'm gonna go through a couple and then let's keep working. All right, so there's a practice test up. Practice test is not required, doesn't go into your grade at all. It's under the category of practice assessments. You can do it as many times as you want. You can do parts of it, you can do none of it, but it's identical to the format of the test. Yes, sir. Let me take a look. Friday. Friday. Put it off. I was gonna do Thursday, we'll put it off on Friday. Okay. Okay, so let's have a look here. So how about something like this? If we're simplifying expressions involving complex numbers, what are we going to do? Okay, say it again.
Do we do the numerator first?
Yeah, we're going to follow, remember, complex numbers are just numbers. All the stuff you've done in the past with real numbers was exactly like this. Real numbers are complex numbers. They just don't have, remember, real numbers are a subset of complex numbers, right? So everything you do with real numbers is exactly the way you do it with complex numbers, only you just don't have the i's in there, right? So we're gonna do parentheses first, right? So on the top, we're gonna simplify this quotient, and then what? Then we just divide, right? We're gonna divide whatever we end up with there. We're gonna divide that complex number by 3 plus I. Okay. So first things first, then. How about this quotient on the top? What are we gonna do there? Okay. So to write the denominator without any i's, we multiply top and bottom by the complex conjugate at the bottom. Right, so we get 2 minus I over 2 minus I. Now on the bottom, this is really quick. What's the answer on the bottom? No? Okay, so let's review this, because that's a pretty quick one. I mean, that one's, I want you to be able to, so we got to hit it again, because you should be able to just tell me right away. So when we multiply complex conjugates, let's not pin ourselves down to specifics, let's be general. So a plus bi represents just any complex number. If we multiply that by its complex conjugate, a minus bi, where a and b are just any real numbers, what do we get? A squared plus b squared. So on the bottom, what's a equal to? 2. What's b equal to? What's the coefficient of I?
0.
No. 1. Yeah. If I just have an x up there, what's the coefficient of x? 1. Yeah, same thing. Remember, we treat the I like a variable. Just think of it like a variable when you're moving terms around and things, right? So a is 2, b is 1. What's a squared plus b squared?
4.
5. Right. A squared plus b squared would be 2 squared plus 1 squared, right? 4 plus 1. So on the bottom, you already know you're getting a 5 on the bottom, right? The bottom's going to be easy. When you multiply complex conjugates, you're going to get a real number, a simple real number answer. Okay, but the top, we got to actually go through the whole process. So if we distribute the -5, what do we get? -10, good. -5 times -I plus, good, plus 5I. 4I times 2 plus 8I. And then 4I times -I. Okay, good. There's our minus 4I squared. What's I squared? So remember, that just changes the sign of that term to a plus 4, right? So that's what we get on top of the fraction. What's that simplify to? -6. We combine the real parts plus 13I over 5. Okay, make sense? Okay, so then that's what we've got on the numerator. Right, so then we've got to divide that by 3 plus I. So now we can, let's try to be efficient about this so we can make it look easier, right? So on the top, everything in the parentheses became -6 plus 13i over 5. When I divide by 3 plus I, that's the same as multiplying by the reciprocal, right? Okay, so we could just multiply that by 1 over 3 plus I, it's plus. And that 5 kind of messes things up a little bit, doesn't it? And that makes it a little bit tougher. But I'm just multiplying two numbers together, right? When I multiply straight across, I'm going to get on the top -6 plus 13i. Let's group that with the 3 plus I. And then this 1/5, let's just leave that out front. That make sense? So we could write it, at least for now, let's just write it like that. 1/5 times -6 plus 13i over 3 plus I. Do I have to do it that way? No. But it does make it look a little easier, doesn't it? So we could just simplify, in other words, we're just going to group these two together as a fraction that we can simplify, right? And then when we're all done, we'll just distribute a 1/5 through, right? No big deal, okay? So how about this one then? What's the recipe for simplifying that quotient? Same thing. So we get 3 minus I, top and bottom. So what's that going to give us? We've got our 1/5 out front. What's that going to give us on the bottom? 10, right? 3 squared plus 1 squared, right? So we get 10 on the bottom. What about if I distribute? So I get -6 times 3. -18. -6 times -I.
6i.
Plus 6i. 13i times 3.
39i.
And 13i times -I.
13i squared.
So -13i squared, which becomes 13. So let's rewrite that then. So we get 1/5 times -18 plus 13 is what? -5?
That is.
6i plus 39i, 45i,
Yeah.
divided by 10. Okay, when all the dust settles. So what can we do now?
Distribute the 1/5.
Okay, we can distribute the 1/5. Before we do that, we could do some. Okay, we'll distribute the 1/5. We'll do it that way.
Yeah.
Is that a good answer?
No.
No, because we want to write it in the standard form of a complex number where we have separate real and imaginary parts. So what do we have to do to that fraction?
5 over 50.
Okay, so what's that simplify to? Good.
1/10. -1/10.
Good. Plus 45 50ths I, what's that simplify to?
5/8. I don't know.
I don't think so.
9/10.
9/10.
All
Alright, there you go. Okay, does that make sense?
Think about it.
Maybe in an alternate universe it does somewhere, but not here.
5/8 is very close, yeah.
Okay, so maybe we don't even have to go through this one, because there's a lot of steps, but let's just talk about what we would do. What would the roadmap be to getting an answer here? Okay, what do you think? Step 1, what are we going to do first? Okay, brackets, right? These parentheses really don't do anything. All they do is just separate that complex number from that one, right? So step 1 is going to be simplify inside the brackets. Then what? Maybe whatever we get from that, we could multiply by that complex number, right? And then finally, I got a 5 I could distribute through, right? Oh, I'm sorry, I missed something, didn't I? What'd I miss? Yeah, I got to square it.
There's no
Okay, I'll wait a bit here. We got a few things to get through. I'd like to get you working. Thanks. So what about the squared? What are we gonna do with that? How do we deal with that?
Distribute it.
You can't.
Oh,
You can't.
oh, it's only gonna make square.
So let's do the first little part of this. I think maybe we won't finish it up, but let's at least start this problem. So if we simplify the part in the middle, we're gonna get 5 times -2 plus 2 is 0. Negative 5i plus negative I is negative 6i. Okay, so in this case, we actually can't, but it's an accident that we can't. So what if we had something like 2 minus 6i squared? You see that we can't distribute there? We can't distribute there because that would be like saying this. That would be like saying that the pattern a plus b squared is equal to a squared plus b squared, but it is not, right? It's not. A plus b quantity squared is a plus b times a plus b. It's more complicated, right? You can't just distribute an exponent when you're adding or subtracting, remember? That's different than this. If I have the product of a times b squared, that is a squared times b squared, right? But you can't do that for a sum or a difference. That's a little tougher, right? We'll deal with that a little later in the year when we do expansion patterns. You're going to know just real quickly what that is. And what, if I take a binomial like that, a plus or minus b squared or a plus or minus b cubed, you guys will just know what those are real quick off the top of your head. But right now, maybe you do, maybe you don't. But it's more complicated than that, right? We have to actually FOIL that whole thing out, a plus b times a plus b. Does that make sense? Okay, so we sort of lucked out here, but you might not on your problem that you get. These are pretty random. If we did have two terms here, if we had both a real part and an imaginary part and we squared it, how would we have to deal with that? We can't distribute. What do we have to do instead? We got to FOIL it out, right? Like, let's just pretend that we had something like 2 minus 6i squared. We'd have to write that out as 2 minus 6i times 2 minus 6i and just FOIL it out to simplify it, okay? Then after that, we could multiply by that other, whatever the result is, we'd multiply by that other complex number. And then when all said and done, we just distribute a 5 through the complex number, right?
Right.
Okay, last one. Let's look at the granddaddy of all quadratic equations here. We can do this, we can do any of them, okay? So what's our strategy here? So, but what are we trying to do? Isolate x because we can point to a single x so we can isolate it. So we reverse order of operations and just follow the roadmap. So first step, subtract 12. So what's that give us? Negative 288. Next step. Divide by 5. Okay, so if I divide each step, or divide each side through by 5, I get the quantity 3x plus 2 squared equals, that doesn't reduce, right? I'm stuck with a fraction. Negative 288 over 5. Now what? Square root. So I square root both sides, and that's going to give me 3x plus 2 equals, what do I have to put every time? Plus or minus. A square root of negative. Okay, so what am I going to do with the negative? What's our rule for that? If I take the square root of negative 288 over 5, let's take an easy example. What if I have the square root of negative 9? What's that become? Not absolute value. It becomes the square root of positive 9 times the square root of negative 1, right? Square root of positive 9 is what? What's the square root of negative 1? Okay, so the short rule then, we don't have to show that step. We just know that when we see a negative inside a radical, automatically that's going to turn into an I outside of the radical, right? So the complex stuff really doesn't make this very much harder. All it's doing is we've got to include that I. Because we had the negative right there, we know that we're gonna get an I at the end, right? We still have to simplify the square root of positive 288 over 5, right? But that's stuff we've been doing anyway. Not saying it's easy, but we've already been practicing that. The only additional issue that we get if we have a negative number under there is that I pops up, okay? So square root of 288 over 5, how do we deal with that? Okay, well, let's split it first of all. We can't reduce the fraction, so we'll split it up into the square root of the top over the square root of the bottom. Bottom simplified, right? We're gonna have to get rid of that radical, but square root of 5 doesn't simplify beyond that. What about 288? Okay, good. So we want to break this down using a factor tree. Remember, we're looking for factors on our perfect square list. Right, etc. Now, if we'd like to get the biggest perfect square possible, I'm going to show you just a little trick here for finding them quickly. You don't have to do it this way. It works without it, but this makes it more efficient. So first thing you obviously want to ask is the number itself a perfect square? Well, 288 is not, right? So then we want to look for the biggest possible perfect square factor of 288. So where should we start looking? Just in general, if the number is 288, what's the biggest number we would even have to consider? Start with lower numbers and work up? You could. I would say do the opposite. I would say you work your way down from the biggest possible number, and then until the first one you hit would be the biggest one, right? So 144. Okay, but why do we pick 144? It just works out nicely this time, but in general, you only have to pick half of that number. So if we were doing this, let's say it was 300. Half of 300 is 150, right? Then you would just go to think of your perfect square list, and you'd start at 150 and work your way up, right? So if we kept going with this list, the next one would be 169. And if we were looking for the number 150, or 300, sorry, half of that is 150. Well, 150 would be in between 144 and 169, right? So all you'd have to do then is start your list from that point upwards and just see which one of those, if any of them, goes in, right? So, if it were 300, we'd probably have to go up quite a ways, probably up to like, I don't know, what it would even be, 25, I guess, would be the first one we'd hit. Or 100, sorry, 100, right? But ours is 288, half of 288 is 144, and so we hit it right away. Half of it is a perfect square. But you get the idea, though? We want to work our way up from the bottom. And I know it's a little bit of extra work, but the payoff is, when you're doing your factor tree then, you've got a big perfect square times a small number. And so, what do we get right away? 12 and 12. Right? So we end up with, so this is equal to plus or minus 12 radical 2 over radical 5 times I. But what do we still have to do with this to rationalize the denominator? How do we get rid of the square root on the bottom? Yeah, whatever the stranded square root on the bottom is, you multiply top and bottom by that. And what's square root of 5 times square root of 5?
5.
5, okay. So finally, we get plus or minus, what's the top become? 12 times square root of 10. On the bottom we get 5. And then afterwards, after the fraction, we'll put our I. You can put the I in the top, but this is better, right? Because we're writing it as some coefficient that's a fraction times I, okay? And then the last couple steps, so, oops. Last couple steps. Subtract 2, right? So when we subtract 2, we're just going to put the negative 2 in front of the plus or minus. Okay, now what? divide by 3. Dividing by 3 is the same as multiplying by 1/3. And especially when you get complicated, you get fractional terms over here, things that don't add up, nicely. You got a real part and imaginary part. I definitely think it's easier to just distribute a 1/3 through the answer. So what do we get? If I distribute the 1/3, I get negative 2/3, right? And then I multiply straight across here, and what would I get? Over 3 times 5, but I can simplify that, can't I? Right? So what's that going to become? 4/5, good. So we get final answer. Well, I forgot my I too.
Oh,
Negative 2/3 plus or minus 4 radical 10 over 5 times I. There they are. Now, what do you notice? Maybe you haven't noticed this. When we solve these quadratic equations, we always get 2 results, right? We've always got 2 results. It's possible you can get 1. We'll talk about that later. But when I get 2 complex solutions like this, how are they related? Negative 2/3 plus 4 radical 10 over 5i, and negative 2/3 minus 4 radical 10 over 5i. What are they? They have the same. Well, they do have the same modulus, but what's the relationship between those 2 numbers? I've got the same real part, and I've got opposite signs of the imaginary. They're complex conjugates. What do you know? Okay, so the two complex solutions we get will always be complex conjugates. Okay. All right, go.